Welcome everyone to another session in the DataHour series. We are excited to have you joined us online for an interactive session. And I'm Raksha Nagaria, part of the data science team at Analytics Vidhya, and I will be the moderator for this 1 hour session. For those who have joined us for the first time, a brief introduction about the DataHour sessions. The DataHour is a series of sessions conducted by Analytics Vidhya, led by top industry experts. And it is a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's a 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment for you all and value adding for our members. Now, on to our speaker in this session of DataHour, we have Razi Ahmed with us. Razi has over a decade-long experience in the data and analytics across a wide variety of domains, including telecom, retail, and banking. He is experienced in executing data-driven solutions to increase efficiency, accuracy, and utility of internal data processing. Currently, Razi is working with AB InBev, world's leading brewing company, as manager data science, where he is a part of the marketing analytics and research vertical. So over to you, Razi. The virtual stage is all yours.
All right. Thanks, Raksha, for the introduction and for setting the stage. How are you guys? Are you feeling excited about the session? Especially on a weekend? I am excited. Although it's a weekend, but learning, we can learn anytime, anywhere. So let me take this time to see what we have done in deep learning and what we where do we see ourselves in deep learning. So when this particular word comes into our mind, when we hear deep learning, we have a lot of things that comes to our mind, right? Like activation function, XYZ, CNN, RNN, all of those things. So much of jargons we hear on a daily basis. But at the end, at the ground level, what we are doing in deep learning is something that we often overlook. So this session is dedicated to that ground level work that we'll do. We will use our pen and paper and we do all the calculation on ourselves. This will make us understand the very basic concept of deep learning, as well as it will give the foundation where we can build upon the complex layers going forward. So like I mentioned, CNN, RNN, all those things, then you can use this foundational knowledge to work upon those layers. So right now we will start the session. A quick introduction for myself. I think Raksha has already done that. My name is Razi. I am working in ABI. It's a brewing company. I think leading brewing company. Working as a data science manager. I have extensive experience in marketing analytics. Over a decade long experience on data science and applying data science into marketing to get efficiency, to get uplift, to get sales and all those things. All right. So, Raksha, how do I share? Okay, I need to share, right? You don't have the material. So let me share my screen.
Yes, you can share your screen.
Let me know if it is visible to you. A quick shout out on the chat. Yes, okay.
Yeah, that is visible.
All right. Okay, so opening the platform. Two things that I want to mention. While we go through the session, we'll definitely going to have some questions, right? So I will say, I will stop in between to take all these questions at certain time. And then you can, if I don't come to your question, then definitely we can connect back on any platform to clear our doubts, or if you have any question on the deck or anything, then we can discuss upon it. I will try to answer all the questions. Maybe in 10 to 15 minutes, I will look up at the chat and see what questions we have, and accordingly we'll take it. At the end, I will open the session for like full question answer. Let me try if I can do that, because the time is really less. I have a hard stop at 3 IST. All right, let's start deep learning. The agenda for today is we'll have a quick refresher where we'll try to see what deep learning is, what are the various building blocks of deep learning, what is a neuron, what is the activation function, and all those things. Yeah, it's here, activation function. And then we'll look at the forward propagation, how it is done, how the data from the input layer, it flows till the output layer. We'll see all the calculations. And then at the same time, we will see the backward propagation, basically how the gradients are being propagated towards the input layer and how the weights are being updated. That's where the learning is actually happening. And then we'll take a simple example where we will pick our pen. So to solve a particular question, a very small neural network, and we'll try to see how the weight is being updated. So I will request you guys to have or to keep pen and paper with you so that you can participate, ask questions, and you can also do this particular example by yourself so that it will be clear to you. Okay. A quick refresher. I think a very simplistic example that you are seeing on your screen. What is a neuron? Sorry. Yeah. What is a neuron? So when we say when we talk about deep learning or neural network, the basic building block is the neuron, right? What you are seeing over here. Can we say this neuron is a set of computational units? You are seeing a circle over here and a rectangle over here, and all of these circle or these shapes, they are doing some computation, right? So basically, a neuron is a set of computational unit, we can say very vaguely. But what is that computation unit they do at the back end? So let's say if this particular unit, we have X as input and we have W as another input. So it will basically multiply these two. So X dot W is what this particular unit is doing, and the output is Z. Then what about this unit? This unit basically is applying a function over the output of previous unit. So Z is the output from this unit, and then we are applying a function Z. So the output is basically f of X dot W, right? That's the output. So this is a very simplistic example, or I would say oversimplification of any neural network. Let's say if we have two examples or two inputs for a computation unit. So X1, X2, W1, W2. It's basically the weighted sum this particular computation unit is doing, and then the output is basically Z, which is being fed into the second unit. And again, we are applying a function f over Z, and that's my output, right? So this is a vague picture of what a computational unit or what a neuron underneath looks like. Often we call this f as activation function, right? So when we say activation function, why do we need it at first place? Why can't we just have this Z as the final output? Well, we will see the reason. But to give you a heads up, this function f basically helps us to learn very complex data. If we have a lot of complexity in the data and it's not something that is linearly correlated, then we need this function to be there so that we learn all those complexity or the complex pattern in the data. So that's where this function will come handy. Let's say we apply this function as something like 2 into Z, right? So it's twice of this Z. So basically we are not doing anything. We are just multiplying this Z by 2, and which is basically, amplifying it. So we are not having we are applying just a linear functionality over here. So to learn a complex function of complex data will not be possible with this kind of activation function, right? Because we are just working on linearity. We have linear combination over here. Again, we are having a linear combination over here. So that's why we need to work a lot upon our activation functions. This will help us to learn complex pattern into the data. Okay. Now we are seeing a better picture of a neural network. We have a lot of inputs here. And we have set of weights. Then over here, we are having a weighted sum. And then again, we are applying an activation function, and that's my output. So this activation function might look familiar to you. It's basically sigmoid. So I'm just taking an example. Sigmoid is an example over here. But let's keep it generic. This is an activation function. This is a weighted sum. And that's how the calculation is being happening. Now, what we want? We want our neural network to be differentiable. We want our neural network to be differentiable. What's the reason for that? The reason for that is, if my neural network is differentiable, if this function is differentiable, then, or my cost function that we will discuss later is differentiable, then we can find gradient. And this gradient will tell me about where the function is, increasing or decreasing. So let's say if I have a function like this, at this particular point, if this function is differentiable, so this will be the direction of the gradient. And if I move in the negative direction of the gradient, I know the function is going to decrease. That's how the gradient is defined. If I move in the positive direction of gradient, the function is going to increase. If I move in the negative direction of the gradient, the function is going to decrease. Now, where do we use this particular concept to decrease a particular function? Well, we use it whenever we have a loss associated with a neural network. So we know loss or the distance, let's say, from, or a diversion from our expected output and the predicted output. We want to minimize that. In that case, we might use gradient, right? And this direction will tell me where this loss function is decreasing. So that's the idea of having this neural network to be differentiable. And then we have in differentiation, we have this chain rule, right? What this chain rule will help us in propagating the differentiation or propagating the gradient function from one layer to previous layer. We will see how we do it in detail, but that's the idea of this chain rule. So you will see that derivative of y with respect to z of this function is, let's say we are having this notation. Then if I want to find derivative of y with respect to wi, I can apply the chain rule over here. So dy by dz multiplied by dz by dw. So that's how I'm propagating the change from with respect to z to with respect to wi. And similarly, change with respect to xi is again I can calculate as dy by dz multiplied by dz by dxi. So what we are discussing right now, we're discussing the basic building blocks of neural network. We'll see how these things will come together and integrate to form a full network. Moving on to next slide. Yeah. Now let's see some common example of activation function. I think you might have already heard of these examples, but the first one, what do you think? What is it? This is the sigmoid function, right? This is a sigmoid function. We often use this particular function as the final output layer whenever we are having a binary classification. Again, I'm sneaking ahead of the topic, but just giving a context. So this is a sigmoid function. How does this, what is the derivative of this particular function? So it's here, f dash z. Basically, this is how we represent derivative. So it's fz into 1 minus of fz. So it's pretty simple. Now, what is this tan h, this hyperbolic tan? Okay, one thing that I forgot. Whenever we apply sigmoid function, it has a good property that the values, the output of this particular function will always lie between 0 and 1. And it's a very important property of sigmoid because we often work with probabilities and the probability space is between 0 to 1. So this sigmoid function can help us shrinking all the values that we have across the real number into a domain of probability. Tan h is a similar kind of function, but the range of this particular function is from -1 to 1. Again, if I know my target values, the range of target values from -1 to 1, then I can easily use this particular function as a last activation function. The derivative of this function is basically given by this expression, 1 minus double derivative of fz. Then we have very famous functionality, or very famous activation function, which is ReLU. Now this is very important. The ReLU function is defined as z when z is greater than 0, or 0 whenever z is less than 0. So you see this, that's how we are having ReLU. I'm very bad at writing, but let me try to give it a shot. So it will go like this, and then it will start increasing. So till 0, we'll have 0 over here. Otherwise, we'll have z. Now, there's one thing that we all have learned in our school in class 11th or class 12th, that this particular point, we are having a sharp curve, and at such point, the function is not differentiable. So at 0, ReLU is not differentiable. But what we said in the previous slide, that we want our neural network to be differentiable. Then what we do with this ReLU? It's not differentiable over here, right? It's differentiable for z greater than 0. It's differentiable for z less than 0. But when z is equal to 0, at that time it's not differentiable. So we have some approximation to help in such cases, and I will show you how. Basically, it should be the next slide. Yeah. So this is a special case where the activation function is not differentiable, right? As you were saying. So what we do is we work with subgradients. Now, what does this subgradient mean? It means we know that this particular point, it's not differentiable, but let's try to draw a tangent at this particular point. That's what derivative or the gradient looks like. It's whenever we have a curve. So tangent to the curve at this particular point is basically my derivative of gradient. Let's try to draw tangents. So now, if I try to draw tangent, there are a lot of lines that I can draw. You see, 1, 2, 3, 4, 5, and a lot more. Now, what do you see common in these lines? All of these lines are having a positive gradient. They are in the upward direction. That means if I move ahead in this direction, my function is going to increase. And if I move in this direction, my function is going to decrease. And that's what we wanted out of our gradient, right? We wanted to know where the function is going to increase and where the function is going to decrease. So we got that, right? We can take any of these approximation as gradient of my ReLU function, and I can work along. So what I need is, this is how derivative is defined. For z less than 0, we are saying the derivative is 0, and for z 0 or greater than 0, we are saying it's equal to 1. So we see at this particular point, although it's not it's not differentiable, but we can take this approximation that going ahead in this direction will increase my function. So that's what we are doing over here, and that's how we are defining the derivative of ReLU. Now, if this function would have been like this, right? Let me draw another picture. I'm very bad at drawing, but let's say if I have this kind of picture. Now, if you try to draw tangents, right? The tangent will change some direction. Now we don't know which approximation to take. So that's the case when we cannot work with this kind of function. But ReLU, we do have some approximation which can help us going forward in the neural network with back-propagation or forward-propagation. So that's what was the concept of this particular slide. Okay. Now let's have a look at the full deep neural network. What we are seeing over here is first layer, which is called the input layer. Then we have hidden layer. We have hidden layer 2, hidden layer 3, hidden layer 1, and then we have output layer. Right? Now, what does this input layer mean? What's the significance of this layer? Well, the significance of this layer is we don't have any weights over here. The weights start from hidden layers. So we can just input our features like age, weight, sales, and XYZ, and we can just impose those features onto the input layer. So that means if I have n number of features, I should have n number of neurons in my input layer. Now it will start from this particular point and it will move. This particular neuron will give input to all the subsequent neurons. So you will see a lot of lines over here, a lot of edges. All of these edges will have some weight. So W1, W2, W3, and so on. And similarly, this neuron will also input to all the neurons, and we are going to have weights different for this. So let's say W dash 2 dash 3 and so on. So that's how this hidden layer are connected. These are fully connected layers. Like each neuron is connected to all the neurons in the next layer, and consequently this neuron is connected to all the neurons of the next layers. Now what happens at the output layer? Now this output layer is basically this output layer is basically what we want the final output to look like. So we are having 4 neurons for now, let's say, but we can have single neuron also, all of them coming together, and this Y as my single output. I can have two neurons at the output, or I can have 4, or I can have 5, any number of neurons at the final output layer. But on what basis do we decide this number of neurons in the output layer? Well, that depends on my target variable, what kind of problem we are basically solving, right? So let's say if I am working on a regression kind of problem where my desired output is a number, let's say I wanted to output 0.01, then I just need one output layer, this Y, right? This will give some output, and this is my expected output, this is my predicted output. We can compare these two, but I only need one output neuron. But let's say if I have a classification problem, a binary classification where I want 0 or 1 output, how I can formulate this output layer? Where there are 2 ways. One, I have 2 neurons, and over here I have 0 or 1 as the output. Over here I have 0 or 1 as the output. Or what I can do is I can have one layer and just 0 or 1 as the output from this layer itself. So 0 means, let's say, class 1, and this is class 2. So that's how we can formulate the binary classification to the output layer. But what if we have multi-class classification? So we have D1, D2, D3 as my output. So that means if there are 3 classes that we want, that I need 3 layers. Each layer will correspond to one of the class. So if let's say there are 4, then that's how D will compare. Over here I'm writing output is 0.1, 0.5, and 0.8. And this classes is D1, D2, and D3. Right? So we might call it as probabilities, or we can also have 0 or 1 as the final output. So what basically we are trying to say over here is how you define your input layer will depend on your features, and how you define your output layer will depend on your target variable. All right. I will take a pause and I will see if there are some questions. I see there are some questions, and some people have already answered to some of the questions. It's a long chat. All right, let's move forward.
I guess there is some questions in the chat section. People have like they have also posted in the chat section. I will pick one for you. There's a question that what happened if the data are infinity, increasing function, but the sigmoid is between 0, 1? And what happens when higher forecast data is used that are never seen in the training data?
Well, this is more about the ethical question in data science. So whenever we are seeing that in our production, we might see some data which the model has never seen or never trained on such kind of data. That means the training data is not the right representation of the production data. In that case, my suggestion would be to remove such kind of outliers. Or what you can do is have a good sample of your production data as your training examples, right? And when you are saying that what happens if the data infinity, so well, we might have to see over here, what if we put z as infinity? So exponential of infinity, let me try to write it. Yeah, so what we are saying over here is 1 plus e raised to the power infinity, right? What this number is basically what we need to check. So you can Google what is the exponential of minus infinity, and then you will get the value. Does that answer to your question? All right. Why backpropagation is required? We'll come to that, Rishabh. We'll see. Why we use 10H? Well, all these activation function is basically defined based on how you want to compress your final output. So for example, as I mentioned in sigmoid, if we want our output to be in the space of probabilities, it can be between 0 to 1. So I can have sigmoid as my function. But let's say my output is from -1 to 1. My target variable is from -1 to 1. In that case, 10H can be a good fit. So it depends whether how you are formulating your column. Now this target variable can be very raw. Like let's say I'm having sales as my target variable. So in that case, the value would be from 0 to 1, 0 to maybe infinity, not infinity, but to a certain range. That can be the sale. But if I'm having, let's say the return on investment, ROI, it can go negative, it can go positive. In that case, I can have 10H as my output function. Getting me? Okay. So let's move forward, and then I will take the questions again. Yeah. So far we have seen a good example of deep neural network. We have seen a single neuron. We have seen hidden layers, input layer and output layer. Now there is one thing that is left in terms of various building blocks. And that thing is basically the divergence function. So over here, we see that this is the output layer, and we, again, I have to write. So this is I'm writing, yeah. So we see that output is 0.3, but my target was 0.1. Yeah, so target was 0.1, the output was 0.3. We know that these two are not close. There is a distance between these two things. So we need to define, or we need to quantify this particular distance, and that's where the divergence function come into the picture. I'm calling it as divergence function, but often you will see as cost function. So what does divergence function do? It basically measures the distance or the difference between your output and your actual target. So let's say we have this D1, D2, D3 as my desired output, and then this is the output which the neural network is giving me. So this function should take input as this particular set of number and this particular set of number, and give me a number which will tell me whether they are close or not, or how far they are, right? So that's how we are defining this divergence function. Here are some examples over here that we are seeing for this divergence function. Let's say we are working on regression problem. Then divergence function can be y minus d the whole square. What is it? This is called as L2 divergence. Yeah, sorry, I forgot the name, but this is L2 divergence, where we are saying y is a number, d is a number. Let's subtract these two and take the square of it. Right. So this will give me a good picture of how far this y and d are. Now, other thing is this this divergence function should be differentiable again. So the derivative of this divergence will be yi minus di. So it's like y of y minus d over 2, this 2 cancel. We have this divergence, the derivative of this particular divergence function. Now we have a classifier. Then the divergence could be log loss, right? So we are saying that minus d log y and minus 1 minus d log of 1 minus y is basically my divergence function. Now, if you see, if I will have d as 1, right? And now output of the neuron, or let's say y is equal to 0.1. We know that these two are very, very far. So we want the divergence to be of higher magnitude. So if you put it over here, you will see this function, this will be 0 because 1 minus d will be 0, and you will left with this number. You will have minus log of 0.1. And if you find this particular number, this will be very high, close to infinity, because log of 0, I think it is close to infinity, and minus of it will be again into the positive side. So that's how log looks like. Right. So this is minus infinity over here, but since we have a negative sign over here, so it will turn like this. So we have very high divergence. So that's how we are penalizing wrong predictions over here. Now, what is the derivative of this particular loss function or divergence function? Let's say, so it's 1 minus 1 over y when d is equal to 1, and 1 over 1 minus y if d is equal to 0. So you can just put value 0 and do a differentiation. So let me just write over here derivative of log y respect to y is equal to 1 over y. You can use it and you can put it into the formula and you will get this particular expression. For multi-class classifier, well, it's the same of the binary classification. Maybe we can have a generalization of binary classification. So it's minus d log of yi. So there are 10 classes. So di would be from 0 to 1 for each of these classes. So it will be 1 for the expected output or for the expected class. For others, it will be 0. So finally you will get the log of minus yc. C is basically the expected class. So what would be happening is, let's say we have 3 classes and this is my prediction. Right, this is my prediction. And my actual class was, this was 1, this was 0, and this was 0. Right. So what this particular divergence function is saying that you take the class which was actually 1. So this is 1, and you take a log of it, log of 0.1, and take a negative sign. So we are again back to the same situation, right? We are again penalizing because we wanted this 1 to be output. So either we wanted it to be highest among this, right? Or we want it to be a greater number close to 1. And both of them are not happening. So we are having a big divergence over here. And what is the differentiation of this particular divergence function? So, well, it's 1 over yc. It's pretty simple because it's just log of yc. So you will have minus 1 over log yc, and for rest it will be 0. Okay. So we have covered what all we have covered. Let's see. We have covered a simple neuron. We have covered how a neural network should be differentiable and why. We have covered some of the activation functions and their derivatives. We have seen why ReLU is a choice, even being non-differentiable at a particular point. Then also we can take work with subgradients in ReLU's case, and it works like a charm. Then we have seen how do we represent the input layer, how do we represent the output layer, and then some of the divergence function that we just discussed. Basically, we want to penalize if the output is wrongly classified or far away from the desired output. Okay, so now we have gone through a good landscape of deep learning. Although it's pretty much simplified, what I have shown over here. You will see whenever you go for some classes or some notebooks or some PDFs, you will see a lot of things over there, right? But I wanted to cover the basics. So now once we have gone through all of those building blocks, let's look at the problem setup. How does we define a problem in deep learning? So we say that given a training set of input and output pairs, so we have x1, d1, x2, d2, xt, dt. So t examples are there. X1 can be a set of numbers representing our features. D1 can be a set of numbers representing the output. So we have for each example of x1 or for each example of x, we have the output defined. Now this is the training set that we call usually in data science, because we know the desired output. Now the error on the ith instance is we have already defined as divergence between yi and di. Now yi is the output of the basically this point. So yi is basically what we are predicting. So this f is what we want to estimate, right? So divergence is basically the distance between yi and the desired output. So we have defined this. We have got training output. Now loss function. So this divergence was for ith record, right? But if we go through all the t records, we have t examples. So if we go through all the t records, we can aggregate all these divergence together, and that would be a mean of all these divergences, and we can call it as loss, right? So this will tell me, okay, in my total training data set, what's the final loss that I am getting. It will give a good understanding of whether my neural network is well trained or not. So that's how we aggregate the divergences for each records. Now this is the challenge. This is what the problem is. We want to minimize this loss with respect to W's and B's. Now what is this W's and B's? W's and B's are the parameters of our neural network, right? So we have W over here, we have W's. So we want the set of W's which can minimize my loss function. That's what we want to estimate through our neural network. I have skipped this B. B is basically the bias that we add, right? So if I add one more neural, so this is, let's say, x1, x2, x3. So I can add this one as a again, and this would be bias. So basically, what we are trying to say is Z is equal to W1 x1 plus B1. So in previous slides, we said that this is a linear combination of our inputs, right? But then we add bias also so that we can learn quickly. And there are other reasons of adding bias. But for now, let's skip this part because, again, I don't want to complicate things. So let's forget about bias for now. We have Z as W1, X1. So with respect to W, we want to find the set of weights which actually minimizes my total loss or loss, however I am defining. This loss is basically the average of all the divergences that I have calculated. I hope it is making sense, right? Okay, let's take a break for a couple of for a minute. Let's see what questions we have on our chat.
So you can also refer to Q&A section. Most of the questions are posted here.
Yeah, right. Okay, there is one question that I can see. How do we decide between ReLU and sigmoid? Coming from Bhupinder. Well, Well, that's the challenge, right? That's where your experience will come into play. ReLU and sigmoid, if you see the differentiation of these two, the derivative or the gradient of sigmoid, it's really slow. It's very less. So the convergence towards the minima or where we want to minimize this loss, it will be really slow. But for ReLU, it's really high because you have Z over here, you differentiate it, it becomes 1, right? So this 1 it's a big number. But for sigmoid, if you differentiate it, you will get a fraction of a number. And that's how it slows down the learning. But nevertheless, you can definitely use sigmoid or ReLU. So that's one thing that can help you in deciding what to use. Okay. So we have set up the problem. We know what we have. We know our building blocks. We know the problem setup. Now the question is, how do we solve it? The first step for that is forward propagation. I think all of you might know about forward propagation, but let me just briefly tell you about it. So what happens is we have these layers in our neural network. So this is layer 1. Let's say this is layer 1. This is layer 2, 3, and this is my output. Right, and this is my last layer. So, and this is my input layer. So what we do is we define activations for each layer. Right, we define the output function. And then we define the divergence. And then what we do is we propagate our inputs into the neural network. So what happens is you see there would be weights associated with this particular edges. And so on, all of these weights. So the first Z that you calculate is basically the linear combination of all the inputs. So Z1 is equal to X1, W1 plus X2, W2, and so on, right? So that's how you calculate Z. Let's say Z comes out to be a number which is equal to 0.3. Now you apply this activation function over this number. So let's say my activation function is ReLU. So I have to calculate ReLU of 0.3. Let me write it over here. ReLU of 0.3. Now ReLU says that if it is less than 0, then output will be 0. Otherwise, the output will be X. So the output would be 0.3. This number is greater than 0, right? So this Y is 0.3. Similarly, we do it for this neuron, and this neuron. We move ahead. We again have this Z as a function of Y's. So basically what happens is, again for Z, we calculate Y1, maybe W1 dash plus Y2, W2 dash, and so on. And again we apply a function on Z. That becomes my Y3, right? This becomes my Y3, yeah, over here. So that's how we do recursively. We take the affine combination of all the weighted, all the inputs, and then we apply an activation function, and then we pass it to the next layer. So that's the job of a neuron, right? We don't need to go into like where this output would be used, what we will do with the output. We don't care. All the thing that this particular neural network cares is take the input, apply a function, and give the output. That's it. So that's how we see, that's how we actually propagate in the forward direction till the last layer. So that's what I have tried to write here in the algorithmic fashion, that input is the d-dimensional vector, which is xj. So this is where I am defining the input, right? So let's say the dimension of it is d. So d0 is basically the width of the 0th layer. Because in the starting, I told you that input layer should be equal to the number of features. That's why we are doing that. D is equal to the D0. Then we are calculating for this particular layer, we don't apply any weights basically. So it starts from this particular point. So we say that xj0 is xj and for all the features. And then for each layer from 1 to n, it starts from this point till n. We do basically zi is weighted combination of the inputs, and then we apply the activation function over the zi. Don't get confused with all the subscripts because it might get confused. But look at in this example on how we are moving forward, right? So again, I will explain. So this is x1, this is w1, and this is f. What happens is x w1 is what it does. Now we move from this layer to this layer, from this layer to this layer till the output. So that's what the overall functionality of forward propagation is. Finally, we will have y, right, as the output over here. Now this y can be a single number or it can be a vector based on how I have formulated, right? We discussed how we are representing our output. So based on that, I can have a single number or I can have a vector. So that's the whole idea of forward propagation. Now the key thing of this particular forward propagation is we need to remember all these intermediate values. Now what are these intermediate values? The values of z's, the values of y's. So you see we over here, we have y calculated, we have z calculated, again for next layer y and z, and all those things. So if there are x numbers, so let's say we remember all these numbers. And it's a very important thing that I'm mentioning over here, that we need to remember all these intermediate values. Now the reason for that is when we back propagate, at that time we will need these numbers. Right? So let's say we have kept in some data structure, we have stored these values so that we can look back to it whenever we need. Right? So that's a key thing, right? Okay, moving forward, backward pass and computing gradient. Let me just have a check on the time. We are really slow, so I will speed up a bit. Let me share it again. Yeah. All right. Now this is the backward pass and computing the gradient, basically the second step. So what we do is, so what we do is at this particular final layer, I have calculated, I know my y, right? So let's say y is 0.3 again, and my d is equal to 0.1, right? So let's calculate divergence, and let me say for now divergence is y minus d whole square 1 by 2, the L2 divergence which I'm talking about. So let's say divergence will be 0.3 minus 0.1 whole square and 1 by 2. You calculate this divergence. At the next step, you calculate the derivative of divergence with respect to y. So basically d of dy of y minus d whole square 1 by 2. So it becomes y minus d, right? You calculate this particular number. So let's say this comes out to be 0.3 minus 0.1, so it's 0.2. Right? Then using the chain rule, basically you calculate derivative of divergence function with respect to z. So right till now we were here, derivative of with respect to y, but now we are moving again backward and saying we need the derivative with respect to z. So with respect to z is equal to d div by dz, multiply by derivative of y with respect to derivative of z. Get me? So you just put dy by dz. I think we have already calculated or not. Oh, sorry. I think I have gone in the different direction. So what we are doing, let me just Yeah. So what we are saying that we have y. So what we are saying that we have y as 0.3 and we have d as 0.1, right? The first thing that we calculate is divergence, derivative of divergence with respect to y, right? Then we calculate derivative of divergence with respect to z. So which is equal to derivative of divergence with respect to y into dy by dz. So let's see how it comes. So derivative of this particular number is 0.1 and derivative of y, basically y was w1 into z1. So we take the derivative of it. So it's equal to 0.1 into the weight w1. We know this weight, right? So we can get this particular value. So let's say I'm getting it as 0.01. So you see, we got to calculate this number, and then again we have to calculate divergence, derivative of divergence with respect to z. We are interested in this particular number, so we'll see how we calculate this using the same chain rule. We keep on, moving backward. So from here to this point, and from this point to this point, and from this point to this w. So we keep on moving backward, and here to here, here to here, till the last layer, where basically we know the derivative of divergence with respect to our input, and we know the derivative of divergence with respect to our weights. So all the weights. While we move forward, we are calculating this number for all the weights in the neural network. And this number basically helps us to, to understand or to intuitionally think that this particular weight is how much it can change the divergence in total. So that's the intuition behind it. And the next time what I will do is, in next iteration, I can change my value of w as w minus learning rate into dy by dw, basically this number, right? So I will update my weight minus learning rate into divergence of derivative of divergence with respect to w. Now this new w will, if you again move forward with this particular new set of weights, you will see that the loss has somewhat lessened. It has already decreased because we have moved in the negative direction or negative gradient of our loss. So we started from here, right? This is my loss, and we are moving in this particular direction, the negative gradient of my loss. So it will decrease the loss in the next iteration, and you keep on doing it, multiple iteration. The loss is going to decrease till a particular point where it gets stagnant, or you basically you expire all the resources and all those things, or the time actually expires. So at that time you stop. So that's the whole idea of backpropagation. Now, often we say that this particular thing that we were saying is all of this particular thing, we often call it as backpropagation, but that's very wrong to say. It might be called as backward pass, but backpropagation is something different to it, right? And unknowingly, we have already used the backpropagation algorithm. Now, what is backpropagation algorithm in raw? So basically, what we are trying to say is, if there is a computational unit and there is a gradient being passed to this unit from some layer or from some anything, and it knows the inputs, let's say w1 and x1, it knows the input. So what it can do is simply is calculate the gradient with respect to w1 and calculate the gradient with respect to x1. So gradient with respect to w1 and again gradient with respect to x1 is what this particular neuron can do very easily. It doesn't need to calculate all of these things together, right? It doesn't need to know where this gradient is coming from. It doesn't need to know where this particular gradient is going from here. All it knows is that if you pass me gradient, and if I know the inputs, I can simply tell you the gradient with respect to w1 and gradient with respect to x1. And that's where that's why we said that we want to keep these numbers, the intermediate number like x1, w1, z1, in some space so that we can look it back. So this is the time where we want to have a look on these numbers. And this algorithm, basically this point where we are saying this gives us a good hand over, computing the functions again and again. So if you see this derivative, so it will be something like that. If you write it in a raw fashion, right? So it will be like f of maybe x1, y1, w1, x2, w2, and so on, right? So that's how it will be nested. And this is just a very simple example we are taking, but we have seen that there are layers, hundreds of layers are there with thousands of neurons. So this complication, this exploding of nested functional loop will actually create a lot of problem when we are doing backpropagation. So rather than that, we just use this particular concept, right? You give me the gradient and I will give you the gradient with respect to my inputs. And that's how we do in TensorFlow or in Keras. All the computational unit that we have over there, they are capable of getting this particular gradient to move forward from themselves. So this gradient basically crosses this neuron and move ahead, right? And from here then to previous step, and from this to previous step, and so on. So that's the overall idea of backpropagation algorithm, and we use it for our backward pass. I think I have really get it dirty, but yes. All right. So over here, what I will do is I will take again some questions, and then we will, work on this particular example. Let me see in the chat board if we have some questions. Right. Raksha, can you help me with the questions?
Yes, definitely. Actually, I guess we are running short on time. We can take a few questions. You can check it in the Q&A section. I will help you to pick. So the first one is, can we have more output features than input features?
It's not a realistic situation, but definitely yes. Nobody is stopping us. So we can have more an architecture which basically goes in this particular shape, right? So from input layer, less number of neurons. From input layer, it can go to a wider number of neurons. We have such examples. We do have some examples from RNN, where we have from sequence to sequence modeling kind of example, where one sentence can actually mean, let's say we are transforming one sentence to another sentence in another language. So a word in one language might need extra words in another language. So that is an example where, from one word we are actually predicting multiple words. So yeah, it can be done.
Okay. Another question is, why DL algorithms, neural networks, require more data for training than ML algorithms like trees, SVM, etc.?
Well, there's a simple reason for that, right? Whenever you work with SVM, logistic regression, the number of parameters are really less. But in DL, you will see a lot of weights are there, a lot of biases are there, right? And then we also have some dropout and all those kind of things. So the number of parameters basically explode. And that's the reason that we need more data to learn or to estimate these parameters.
Okay, another question is, can you give a real life example to differentiate between recurrent neural network and backpropagation?
Yeah, this is complex. I actually don't want to move into RNN or any advanced version of deep neural network, because it will actually confuse people who are getting to the platform and getting to understand all of this thing. But for this particular case, we can have a different connect where we will talk about advanced stuff, and then we can explain, right? Right now, let's park all the RNN, CNN, transformer, and all those questions aside for maybe next session, right?
Okay. And what is the thumb rule to select activation function for classification regression kind of problems?
Well, there is no thumb rule. To be very honest, there is no thumb rule.
Mhm.
More of it is on a trial basis, and some of them it's on intuition basis. Raksha, let's. I need 10 more minutes to take the audience with this particular question, and that will really help them. Right?
Okay,
And
okay, no issues. Yeah, you
yeah.
can carry on.
Sorry guys for people whom I could not take the questions, but I will definitely connect in some other session and see. Yeah. Now what I want you guys to do is take a pen, take a paper, and let's try to see how we can solve these examples. So it's a very simplistic neural network. We see that we have only two inputs, x1 and x2, right? And it moves forward, and the edges that we have, they are having weights w11, w12, 21, and all of these weights, and we have the values of all of these weights. Okay? Maybe this is how the weights are initialized. And then we calculate Z1, which is basically the pre-activation input. And then we apply the activation over here, and then we get the Y1. Similarly for Z2, and then we get Z2. And these two neurons are giving the input for the output layer as Z0. And then the activation over here is a square function. And then we have a divergence. We get this output Y, and this Y is being fed into the divergence, and where we get that desired output also. So we compare Y and D in this particular function, and then we move backward again with the derivatives, right? So we will update this W11, W12, and W21 through the derivatives. But what I want you guys to tell me the value of Y if you move in this forward direction. Can you help? Can you help with that? So let me just give some inputs over here. So what we want to do is, let's say this Z1. Now Z1 is a combination of X1 and X2 weighted by W11 and W21. So it will be X1 into W11 plus X2 into this weight 21. So that means, so we have X1 as 2 and 3. It's a toy example, so don't go on the numbers. So 2 into 0.2 plus 3 into 0.4, and this will come out to be 0.4 plus 0.16. I hope my calculation is right. So you got this value as 0.16. Now let's say activation is Y, ReLU. So what will be Y? Can you tell me quickly? I'm opening my chat window also side by side. Guys, what will be the value of Y1? Thanks, Ashok. Yeah, that's correct. And then what will be the value of Z0? Well, W1 is 0.9 multiplied by 0.16. Oh, we need Y2 also. So Y2 will be, for that we need Z2 also. So Z2 is equal to what is it? X2 value is 3 into what is W22? W22 is 0.5. This 2.1 is for this particular Z2 plus W12 is 0.3, so 0.3 into X1 is 2. So yeah, I think so 15 and plus 6, so it's 0.21. Then Y2 will be equal to 0.21 again, because we have the ReLU over here, right? So Z0 is, we had this particular weight, and then let's multiply 0.21 with weight W2, which is 0.8. I want you guys to tell me this number, whatever it is. 13 plus, okay, yeah, 2.17. Right now, I'm not focusing on the number. It might look very off also, because this is a toy example I just took out of my mind only. So this number, let's say, again, we have some number over here. If you can give me 11.6, okay. And this divergence. And okay, so this is Z0, right? We have got Z0 as 11.6. Then Y is basically the square function. So Y is 11.6 whole square. So it comes out to be 121 point something. Let's take it as 121. Now, can you tell me this divergence? It's mean squared error, so it's basically Y minus D whole square and 1 by 2. So it's 121 minus 0.001 whole square. So you can get this number as, let's say, 120. So we have got this divergence. We have got all the intermediate values, right? We have got all of these things. So our forward propagation has been completed. Let's move in the backward direction now. So first thing that I need is derivative of divergence with respect to Y. So this is my divergence function. If I drive it, so it will come out to be Y minus D, and it will be 121 approximately. Then I want the derivative of divergence with respect to, let's move back, with respect to Z0. So can you tell me what this would be? Is the chain rule correct? I think yes. So we know this value, and we can calculate this value. So it's equal to 121 into derivative of Y. Y is basically square of Z, right? It's square of Z. So we can say 2Z. Now I know this value of Z0. Z0 is 1.16. So what I can do is 121 into 1.16. So I'm just scaling it back to a good number. So let's say we get the value as 2. Right. So what we have done, we have got the derivative of divergence with respect to Y. We have got the derivative of divergence with respect to Z. And again, we want the derivative with respect to W11, W-1. So let me write it over here. So how can we get that? If you can help me. So it would be divergence of Z0 into derivative of Z0 with respect to W1. So divergence of this we already got as this number 2. So we can say 2 multiplied by derivative of Z0. Now Z0 is a linear combination of W's. So we can write Y1 into W1 plus Y2 into W2 with respect to weight. This number will be 0 because there is no W1 here, and we will have Y1 out of this. So we will have 2 into Y1. So 2 into, we know this value Y1, right? I have already told you that we need to store all these intermediate values. So Y1 is 0.16. So it's 3.2. So that's how basically we got the first update in our, not the update, but we know that how this weight is changing my divergence. In the next iteration, what we will do is we will get the new value of W1 dash as 3.2. Sorry, the previous value of W1 dash was this number, 0.9. So we'll have 0.9 minus, what is the learning rate? 0.1. So 0.1 into this number 3.2. So it's again 0.3, so it's 0.6. So that's the weight in the next iteration. And again, we can get with respect to this number, with respect to this. I wanted to actually show the full example, but nevertheless, we have got the first the derivative with respect to first weight. Similarly, we can backpropagate each step. Like over here, we keep on moving backward. We just multiply with the previous gradient, right? So over here also, this was the previous gradient that I was getting from this point. So I just multiplied this with the derivative of this number. So that's how this backpropagation help us into, to avoid a lot of computation, because otherwise we would need to compute this number again and again. But let's say from here, W1, we again go back to this particular layer and this particular. So I will leave this this example to you guys so that you can work upon it. Maybe you can take a screenshot, or it's really dirty, but you can take a screenshot and try it on yourself. It's really easy to do it. And once you do it, you will feel a lot more confident. We are running out of time, so I will stop this example over here. Let's see what I have. So this is it from my side. But if there are any questions, let's go into the question and answer session for 5 minutes. And what I want you guys to do is, attempt this particular example, update all of these weights together, and then again the next iteration, see what is the value of divergence. It should come down. That's how basically we perceive. And with lot of other iterations, it will come down to a minimum.
Okay, Rosie. Yes, sorry to interrupt. So before we head towards Q&A section, I would like to request the attendees to please please participate in the feedback poll. It helps us to conduct such more sessions. I'm shooting a poll here. I would like to request everyone to participate in this.
Yeah, I'm just giving the full screen of it. Anyone, if you want to take the screenshot, then just take it. And I think, Raksha, this particular session would be available as a recording also, right?
Yes, it will be available in our YouTube channel. Okay, so till then we can take a few questions if you want to.
Let me see, where do we see questions? The question is, how do we decide in DL maximum number of layers so that performance is not degraded? Well, again, it depends. There is no thumb rule, as I mentioned, but the architecture, to get it right, you need to see what is the number of input records you have in the training data set and how complex is your data. So let's say if we are going with maybe a sequence, right? Or let's take a simple example. Let's say we are predicting the sales. It might not be very difficult to predict the sale, right? In a forecasting example. So we might not need lot of layers. We can simply have 1 or 2 layers, and then we see how the error looks like. I think that's how it depends on your data complexity, I would say. there are many industry-sponsored deep learning frameworks in the market. What are the use cases where some library performs well, again, there is no thumb rule. I would say, I would suggest you guys to not look upon the industry-sponsored deep learning frameworks and rather focus on uh, your custom networks. You build the network on yourself and try to create this architecture on yourself. It will give you good understanding, and then maybe you will be able to apply these high-level framework in a better way. How can we be sure that subtracting derivative of weights will help in minimizing the error in long term? Well, this is how the whole intuition started, right? It's Samrat. So that's how the whole intuition started. We knew that gradient always points in the increasing direction, or in the direction where the function increases. So negative gradient will always point in the direction where the function is decreasing. And we know that we have calculated derivative of divergence with respect to weight. And that's why we are moving the negative direction, right? Although, because we are taking one record at a time, so you might see a lot of zigzag in your error term. So your error term might come down with a trend, but it will have a lot of zigzag values while coming down, because we are taking one example at a time. So to counter to that, you can take a group of records together. So let's say you are taking 10 records together, and then you are updating the weight. So I think it is called as batch gradient. Yeah, it's called as batch gradient. So that helps in smoothing this zigzag. With deep learning, we usually need large training data. How to balance between computation cost and optimization? If data is less, there is chance of overfitting. Well, I will not say if data is less, the chances of overfitting is there, right? Overfitting happens when you learn each and every pattern of the data, and that happens when you have a lot of data and you have all the representation of the production data. So that happens with such kind of scenario. But in deep learning, we usually need large training data. How to balance? Well, computation you need. So how to answer this? Well, all of the computation, if you see, all of these are very simple computation. It's not complex. Yeah, most of them are matrix multiplication, right? So to come up with a time efficient computation, you might need to go to a infrastructure where this computation can be accelerated. So that's where the GPUs come into the picture. So these GPUs are built to accelerate such kind of operation where we are just multiplying some number or we are just adding some number. Overall, that's what we are doing, right? In all the deep learning or all the forward computation, backward computation, we are just multiplying number, we are just adding number, and that's it. So let's move to the framework which accelerate such kind of operations. Difference between divergence and error. Well, it's synonym to each other, so not actually any difference. It's just one thing that divergence is something that you define a function based on how you want to penalize the wrong predictions. Well, I think I am really short of time now. Let's look at the poll, and yeah, we can have such these questions. Maybe you can send them through email, and I will reply to them.
Yes, I guess we are already running short on time, and either most of the questions are they repetitive or they are covered. So thank you so much, Razi, on the behalf of Analytics Vidhya. Thank you so much for joining and delivering such a wonderful session. And I hope that it is our audience might found it insightful, and it was really a great session.
All right, thank you guys. Really, just one thing that I want to mention: focus on the ground level things. Don't go into too much of advanced stuff that is going on in deep learning. That will really confuse you a bit. And once you know the ground level things, I think then the stage is right to move to the advanced things. So that's my closing note, I would say.
So thank you so much for joining, and I hope our audience, yes, sir, it would found insightful, and hopefully we can conduct more such sessions with you in the future.
Sure. Thank you guys. Take care.
Okay, so audience, we are wrapping up the session here, and thank you so much for participating in the polls and sharing your valuable feedback. We will meet again in the next webinar.